All right, hello everyone. We're going to continue on here as if we were in class, but now it's on YouTube. So remember, last time we talked about the power rule that said if we had x to some power, all that we did was take down, if we're trying to take the derivative, we take down the exponent and then we write x to the one less power. Now, then we discussed what the coefficient rule was. So if we had a coefficient, so some number like 7 times a function, and we wanted to take that derivative, the 7's along for the ride, the constant's along for the ride. So then we just take the derivative of the function, and then we get the derivative of the whole thing. Then if we add two functions, so our addition rule, all we do is we can take the derivative of the first plus the derivative of the second. And then similarly for the subtraction rule. So I wanted to do a quick remark here where it says if y equals f of x, then the derivative is y prime, which equals f prime of x. And then we could also use this new notation dy dx. Now this is called Leibniz notation. And basically, when Newton was creating calculus, Leibniz was also creating calculus at the same time. And so Newton used the prime method and notation, and then Leibniz had this new notation, dy dx. And basically it's just saying the derivative of y with respect to x. Okay, so I try to avoid writing y prime because sometimes if you go real quickly, you might think that it says y to the first power, and then you might want to take that derivative. So just to avoid that, I try to write f prime of x or dy dx, and that's just a personal preference. Okay, so now we know how to take our derivatives of powers of x. However, there's other functions out there. So for example, we could have some trig functions. And what are the derivatives of the trig functions? So the way we can discover that is by actually diving into what the definition of the derivative is. And so that's actually what we're going to do right now. We are going to prove what the derivative of sine x is. In order to do that, we need to recall a couple properties of the trig functions. So the first one is what sine of x plus y is. Now you might have seen this. It's just a property, and you may have proved it before in your life. But if you don't remember what it is, you could just Google it, and then this will come up. We get that it equals sine x times cosine y plus cosine x sine y. And then there's a similar one for cosine. So cosine is cosine x cosine y minus sine x sine y. All right. Then next, we also want to recall we have the limit as x goes to 0 of cosine x minus 1 over x equals 0. I believe we did this in class. What would you do? You substitute in 0, you get 0 over 0. So you multiply by the conjugate of the top and then use the property sine squared x plus cosine squared x equals 1. And then you can figure out that when you evaluate the limit, then once you do all the substitutions, then you get 0. So let's just believe that that's true for now. And then now we're going to find the derivative of sine x. Okay. So some of you might know what it is, and in that case, maybe challenge yourself to see Well, do you actually know why? It's the derivative of sine x is what it is. And that's what we're going to show today. So here we go. So we're going to have f of x equals sine x. That's our function. We're going to find its derivative. And for that, like I said, we need our limit definition of the derivative. And don't worry, once we do this, then we don't have to do it again. So let's take it one step at a time here. Let's write f of x plus h minus f of x over h. Then we have the limit as h goes to 0. We have our function is sine, and then we replace x with x plus h. Then we subtract sine x over h. Now we're going to use that first property that we recalled here to replace that sine of x plus h. So whenever I see a y, I'm just going to write h. So we have that equals sine x cosine h plus cosine x sine h minus sine x over h. Okay, so now what I want to do is, I notice that there's two terms that have a sine x in them. I want to write them next to each other. All right. Now what I want to do is let's factor out a sine x from the first two terms. So I'm left with cosine h, and then when I factor sine x out of the second term, we just have a minus 1 left over. And then we have our third term that's kind of along for the ride for the moment. Okay. So then we have limits have this wonderful property where you can split it apart. And by that I mean we can write sine x. Well, we got one term in the denominator, so let's split it apart like this for the moment. H plus cosine x sine h over h. Now we can do that because there's one term in the denominator. If there was a couple terms in the denominator and only one term up top, we couldn't split it apart like this. And then let's write it like this, and I want to keep that property up there. So that's why I'm writing it over here. And then the limits we can split apart, like I said before. So we get sine x, and then we got cosine h minus 1 over h. So I'm kind of splitting it apart, but you'll see why here in a second. H going to 0, we get cosine x sine h, and then let's do that part over h as well. Okay, so then we can see that up here we had this property that cosine, we have instead of x we got h. Cosine, the limit as h goes to 0 of cosine h minus 1 over h, that thing is going to go to 0. Just from that property above. And then we also know that the limit as h goes to 0 of sine h over h goes to 1. Like what we got when we proved it in class using the sectors of circles. Okay, so then what does that say? Well, the first limit is h goes to 0, we have sine x times 0, and then plus the limit as h goes to 0 of cosine x. Right? And then we have 0 times sine x, so that's 0. And then the limit as h goes to 0 of cosine x, well, there's no h's there. So it's just cosine x. And there we go. Now, isn't that crazy? I knew that sine was related to cosine, but I would have never thought that its derivative was cosine. And there we go. And that's what we want to memorize here. And now we don't ever have to do that ever again.